Welcome to Steady Degassing Solution. My name is Bharat Sharma, and thank you very much for your support. And in this metal safety webinar series, we are keep on continue to explaining how we can melt safely and what is the good practice which we have to use during the molten metal or melting aluminum, zinc, and magnesium. So now today we discuss about the molten metal treatment. Molten metal may need to have impurity or inclusion removed. The cleaner the metal, the better the casting characteristic and physical property of the final casting. Many methods can be used to clean the molten metal. It depends on what you are trying to remove or charge. The goal of treating the metal is to improve the quality of the casting. And after completing this video, you can able to identify when to use specific metal treatments. You can able to identify the 5 methods used to degas the melt, and you also able to identify the benefit of each metal treatment. You are able to identify the type of chemical compound fluxes and the 3 process used to remove solid inclusion. This information you can use to provide a specific instruction or treating molten metal. You can use this information to improve the quality of casting. Okay, let's discuss about the demagging. Demagging is a very different word nowadays. So demagging is the process of removing magnesium from aluminum alloy scrap. This practice is common in secondary smelting operation and used by the die caster only in plants that are large enough to support scrap recycling and reclamation activities. Demagging is done to reduce the magnesium content of 380 alloy to the specified 0.1%. Typically, other aluminum alloy composition, both cast and wrought iron alloys, contain subsequently greater amount of magnesium. The secondary melter must use these various alloy in consumer scrap from as a feedstock for their smelting operations to produce the specification die cast alloy compositions. Chlorine and fluorine. Magnesium removal from aluminum is accomplished by application of chlorine or fluorine compound which react favorably in aluminum according to the this following equation you can see over here. When chlorine gas Cl2 is introduced into liquid aluminum, it reacts to form aluminum chloride AlCl3. The aluminum chloride react with magnesium 2, then form a magnesium chloride MgCl2 and aluminum. The magnesium chloride then flows to the top of the metal bath and is removed in the drawers. Aluminum acts solely as the carrier for this reaction. Chlorine is the preferred reactant despite the warranted environmental concern. Chlorine achieves the best productivity, especially in demagging large furnace batches such as 1 lakh pound rebreattery furnaces. Typically, the chlorine is applied through a gas injection pump, as you can see in this image. Okay, now let's discuss about the demagging removal process. The centrifugal style pump is set into a sidewall furnace, as you can see in this figure. Alright, the action of the rotating impeller 300 to 800 rpm shares the incipient chlorine gas bubble that are injected through the lens just ahead of the impeller. This creates a large swarm of a very fine sized bubble with the high surface area to volume ratio. The greater the surface area, the better the reaction with magnesium in the melt. And you can see this process in this image. The magnesium chloride, which is lighter than the metal, will rise to the trough and must be skimmed off. Often a thickening flux compound is added to the draws, which is a liquid pastry, to facilitate this separation. When the gas injection pump is used properly, the reaction is highly efficient and minimal free chlorine or chlorine byproduct compound are created. Environmental compliance has been achieved by many die casters using this technology. Okay, now let's discuss about the demagging efficiency. Despite the actual efficiency very near 100% for the demagging process using the gas injection pump versus an earlier technology that employed a static injection lens and a bell to collect fumes plus a wet scrubber, efficiency is measured by amount of chlorine utilized to remove a pound of magnesium compared to the theoretical value, which is 2.95 pound of chlorine to remove 1 pound of magnesium. Alright, so let's move ahead and discuss about degassing. It's nowadays commonly this process are using by many die casters. So aluminum die cast alloy composition can readily absorb hydrogen gas from a variety of sources. Historical hydrogen content in aluminum die casting was not considered a problem. Today, even a higher quality demands thinner section, and engineering structural casting often demand hydrogen be removed prior to the casting process. This is despite the fact that the fast solidification process may often depress any resultant porosity or micro porosity. Degassing techniques. Assuming hydrogen is present and must be removed, there are several methods to degas the melt. First is natural outgassing. As the temperature of the melt drops, there is less solubility of the hydrogen in the liquid metal state, and some hydrogen will be lost by this method. It's a natural outgassing, nothing you have to do in that. So second one is chemical fluxing. Historical a product called a degassing tablet is applied. This tablet contains C2Cl6 hexachloroethane, which upon contact with molten aluminum decompose to release chlorine. The chlorine react with the aluminum to form a gaseous phase aluminum chloride. These gas bubble, which are metastable, rise through the melt, as you can see in this image, and these gas bubble which are metastable rise through a melt. Hydrogen atoms diffuse through the interface from a hydrogen molecule inside the rising gas bubble, and when the bubbles reach the surface or draw spaces, the hydrogen is released back into the atmosphere. Tools to plunge a solid tablet or to inject gas through a fluxing tube, you can see in this second image. With either technique, it is important to plunge inject the gas source as low into the vessel as possible below the melt surface. This maximizes the reaction time. The time it takes the rising gas bubble to eventually reach the surface of the melt. Third one is inert gas fluxing or flushing. A gas such as argon, nitrogen, or both with a small amount of chlorine is injected into the melt with a flux tube or lens, as you can see in this image. The injected gas bubble, this time inert, collect hydrogen in much the same way as the aluminum chloride bubbles does. When chlorine is added to an inert gas, there is an easier interface. For example, diffusion path for the hydrogen atom to travel, and hence chlorine addition can facilitate hydrogen removal. Fourth one, porous plug technique to remove hydrogen gas. These are cast into the bottom of a ladle or deep well. Replacement necessitate taking the ladle or furnace fully out of service. It's not, I think, most popular or technique for degassing. The most popular technique is rotor degassing, which is the fifth technique of this video. So this may also be coupled with flux injection. Today the most effective degassing technique is to use a rotor degassing device, and you can see in this image rotor degassing produce a much smaller size pure gas bubbles than does static lens. The smaller the bubbles, the greater the surface area and slower the rate of rise through the melt, which combine to produce higher degassing efficiency. This can be demonstrated in a water model, which it can be in which it can be seen that there is a wider swarm of many more smaller bubbles with the rotating device. The same effect can also be achieved, but with less pure gas metal mixing by using a very fine pore size porous dispenser on the end of a static flux tube. Degassing capability are compared. Note that a rotor degassing process outspaces either a static lens or even a porch plug in reducing the hydrogen content. Okay, if we talk about the degassing benefits, so degassing has a beneficial effect on melt cleanness, gas fluxing remove hydrogen, and also float Al2O3 inclusions. When chlorine is added to the inert gas, there is an enhancement of inclusion removal. The chlorine lowers the surface tension between a solid oxide particle and the aluminum melt, facilitating the ability of the gas bubble to grab the inclusion. Okay, if we compare all these techniques, all three techniques, lens, porous plug, and impeller, right? So furthermore, since oxide particles themselves can hold on the hydrogen atoms, any cleaning technique that assist in removing inclusion can also lower the hydrogen gas content with a resultant decrease in porosity. Okay, so let's discuss about the fluxing. Fluxing the metal can be done in a different way. First is apply chemical compound to bath during the melting process. Second one is insert inert gas by means of vent, lens, or pipe. A flux injection or any flux particle at all should never be applied to a holding furnace in the casting dip out well, as any residue will find their way into the die casting themselves. Flux residue cause spotting, surface defect, corrosion, and porosity in casting. Okay, so first we discuss the chemical compound fluxing. The commercially available fluxes may perform one of the more specific function. Not all fluxes are the same. Fluxing composition consists of reactive components, fillers, extender, etc. to provide specific physical and chemical properties, provide body and reduce cost. Flux compound should be used to at the addition rate specified by the manufacturer. Okay, in this sheet, halogen compounds such as chloride and fluoride are predominant because these compounds form useful mixture at a molten metal, molten aluminum temperature. For example, this you know image display temperature that is below the liquid of many aluminum die cast alloy. This become important in considering flux function. Okay, now let's discuss about the chemical compound fluxing composition. Flux compositions may be critical to a certain alloy. For example, fluxes containing sodium salt should never be used with aluminum magnesium alloy, or the hypothetic 390 because of adverse reaction with the metal composition. It caused the creation of inverting sodium containing precipitates in the former and interface with the phosphorus, the silicon modifier in as a metal cleaner or modifier and grain refiner. Type of chemical compound fluxes. There are principally 5 type of chemical compound fluxes: cover, drossing, wall cleaning, degassing, refining. So cover flux. So first of all, discuss about the cover fluxes. So cover fluxes are used to cover the melt. This provides some protection from rampant oxidation at the melt surface, and as most cover fluxes go liquid, serve to collect compound dirt and other non-metallic materials from scrap charges. So first of all, we have to understand that each type of fluxes has a unique application. So there are 5 type of fluxes are being used in melting process. So each flux we have to use as per their application. So let's discuss about in some deep about each type of flux. So first we discuss cover fluxes. Now we discuss Degassing fluxes. So Degassing fluxes are used to lower the metallic content of dross, which is the surface oxidation product that occurs at the bath surface during melting. Dross information can be quite substantial, and further heat transfer into the bath through this phase can be diminished. Degassing fluxes contain fluoride that lower the surface tension at the interface between aluminum and aluminum oxide. The Degassing fluxes provide a localized exothermic reaction that raise temperature and increase fluidity. In this image, the reaction is linked to a M&M candy, showing how Degassing flux help physically break up the hard shell which surround the soft candy entrapped, you can say entrapped aluminum. The proper Degassing flux practice can reduce the metallic content of dross, often about 85% recoverable aluminum to 35% or substantially less, thereby resulting in a significant saving to the die cast operation in useful metal recovery. To properly utilize Degassing flux, which show this image show a dross layer on the charging well of a laboratory furnace. So first step is spread the Degassing flux evenly over the dross layer at the rate of about 1 to 2 pounds per square yard. 1 to 2 pound per square yard. This is the important parameter you need to keep in your mind. So how you spread, in what quantity you can spread it, 1 to 2 pound per square yard. Second step is chop, rake or rabble in the flux slightly to start the reaction. Avoid bringing fresh metal into the dross faces, thus the emphasis on artful racking and rabbling. Third step is when the flux has truly reacted as evidence of waning of the visible exothermic reaction, spark and small fires, continue racking, rabbling to allow the now free metallic content to fall back into the bath. A powdery dross residue show result. Correspondingly, this image unfluxed dross will be have a very metallic looking appearance as shown in this figure. Okay, now let's discuss about the wall cleaning fluxes. Wall cleaning fluxes usually contain ingredient that physically soften buildup of oxide and dross layers attached to the furnace walls, thereby enhancing removal with a scraping tool. Wall cleaning fluxes are often applied with the gunning device to achieve intimate contact of the flux with the walls. Wall cleaning is the best practice at a low heel condition where the walls are exposed. The flux will soften the wall buildup, provide corundum growth as not proceed too far, such that the removal with the spudging tool is possible. All residues should be thoroughly removed from the furnace during the cleaning operations. Several degassing. Let's discuss about the degassing, because the another type of flux are used in degassing. So that there are solid fluxes that when applied provide degassing by means of decomposition of gas bearing constitute the inert gas serve the collect dissolved hydrogen. So refining fluxes. Refining fluxes may include materials that provide either grain refiner or modification. A favorable alteration of aesthetic silicon structure in a hypothetic die-casting alloy, or of primary silicon structure in a hyperethetic silicon alloy. Fundamentally, the only common element found in aluminum die-casting alloy composition that is chemically refinable is magnesium, owing to its favorable thermodynamic possibility using chlorine or fluorine as a reactant. Chemical flux storage. So let's discuss about the chemical flux storage. All flux should be stored in clean, dry, closed containers at a reasonable ambient temperatures. Many fluxes compound are hygroscopic and thus will pick up moisture. This is really source of hydrogen when placed in contact with the molten aluminum. Also, it causes spitting and popping, which is a safety issue. Fluxing practice and dross treatment. Dross is a mixture of oxide plus entrapped metal and is formed during all melting processes. The quantity of dross formed during melting growth with you can say first is increasing furnace temperature, second is possible, these are the reason to grow dross. Increasing furnace temperature, second one possible gas impingement in fuel fired furnace, third one type of condition of the metal charge that will always contain oxide skin, fourth one turbulence during charging. So dross fluxing frequency, Fluxing frequency in a melting furnace will depend on the individual operation. A procedure should be put into place and followed regularly. With continuous melting operation, skimming and fluxing are necessary at some intervals to prevent dross buildup from retarding the heat transfer and the resultant desired melting rate, as has been mentioned. Dross recumulation. Many die caster may prefer to directly skim the dross from a melting furnace and either sell it to a metal reclaimer or treat the dross outside the furnace. Not using a fluxing practice within the furnace does have some degree of merit, as salt flux attack on a refractory will reduce the time between relinings. However, decision must be made as to how to achieve the best economic of melting and metal recovery. Dross volume can be 2 to 6% during melting, with as much as 85% recoverable metal content. If only skimming is practiced, there are two ways to save the available metal in the skim. One is spread the dross out so that it cools, otherwise exothermic reaction can continue and will burn up much of the aluminum melt still contained in the dross. Another method is to utilize a dross recumulation system. You can see in this image, or you can also watch dross recovery complete video, which is available in 2 parts on our YouTube channel. A dross recumulation system is especially useful for small operation. A small amount of flux can be easily added into the vessel and stirred in the allowing the feed up aluminum fire to the drain into ingot mold below. The remaining powdery dross can be dumped out, sprayed and cooled. Approximately 1% to 1.5% metallic may be left, which may be sold for further recumulation. For larger die-cast operation, there are dross cooler available. These are essentially steel containers that can be atmosphered with argon to facilitate cool down without further oxidation. A recent development include a dross press, as shown in this image, that physically force entrapped liquid aluminum from the mushy dross. Okay, let's discuss about the fluxing injection. One of the more useful melt treatment technology to have recently evolved in that of flux injection. In the flux injection process, solid chemical fluxing agent are injected with the carrier gas, usually nitrogen or argon gases. Flux injection has a several benefit over manual flux addition. First is less pledge, second one better environment compliance, third less flux uses, fourth greater reaction benefit. Flux injection or any flux practice at all should never be applied to a holding furnace in the casting dip out well, as any residue will find their way into the die casting themselves. Flux reduce residue cause spotting, surface defect, corrosion and porosity in casting, and this thing also we discussed earlier in this video. Alright, let's discuss about this flux injection with rotor dispersion. When flux injection is coupled with the rotor dispersion, as you can see in this image, better results are obtained. In this situation, the mixing kinetic between flux agent and the metal bath are increased, as the rotor action create much better dispersion than a simple static flux injection. Flux injection with rotor dispersion is usually practiced to achieve degassing through both the flux compound and the carrier gas itself. In addition, proper flux composition will help clean the bath by combining with oxide in the metal to a great extent and delivering many of these to the surface ready for skimming. One of the principal benefit of combined flux injection rotor dispersion technology is effect on dross content. Any fluxing or rotor dispersion create dross. This is because not only is there some turbulence involved in the metal bath, but more importantly oxide are brought to the surface. Despite the difference in metallic content of the dross resulting from the rotor degassing and flux injection, each alone and in combination, in essence application of the proper flux compound reduce the dross, resulting in a lesser quantity of dross and subsequently lower metallic content of the dross and remains. Now let's discuss about the filtration. Filtration is increasingly being used by aluminum die caster. Filtration is necessary to remove inclusion to meet the high quality demand of many die cast products, especially automotive component. Several of the beneficial effect of filtration we can discuss here. The first is improved casting fluidity, second better machinability, reduced porosity, better surface finish, higher mechanical properties, reduce reject or rework, increased profitability and product marketability. Filtration and solid inclusion removal. Filtration is the only one of three processes by which solid inclusion can be removed from an aluminum melt. The other two are sedimentation, the settling of inclusion that are heavier than the base melt. Flotation, the rising of lighter inclusion than the melt to the dross phase where they may be skimmed. These two processes may not always be available. Sedimentation involve holding time, which reduce productivity. Also, any pouring operation can re-steer sedimented inclusion back into the main melt. Flotation inclusion rise can also involve long holding time and the application of degassing and or flux injection to accomplish the purpose. Both degassing and flux injection are dependent on through skimming to remove the accumulated dross. In addition, many inclusions have a density very similar to that of the base melt and hence will neither float nor sediment and therefore must be removed by other means. In this image, the microstructure of an unfiltered versus a filtered die cast alloy, there is much cleaner microstructure in the later, wherein the inclusions, principally oxide, have been removed. Filtration benefit. The ability of the liquid metal to fill the die cast cavity and especially thin section intricate shapes can be greatly affected by filtration, improving the metal fluidity. The greater fluidity results from the filtration process, removing the solid inclusions that are hindrance to smooth metal flow. Filtration has been observed to significantly reduce reject, improve mechanically properties, to eliminate hard spot and to be cost effective in many die casting operations. Also, a hard sludge particles detrimental to machining operation can be successfully removed by the filtration process. One of the more important aspect of filtration is its effect on metal fluidity, as you can see in this image. Okay, let's discuss about the filtration type of and forms. Unlike sand and permanent mold foundry processes, metal filtration cannot be employed in the mold in the die casting process. Consistently, several forms of in furnace filtration have been developed that provide filtration as close to the casting source as possible. This may include filtration in a central metal breakdown furnace, melting die cast scrap, trim gate and runners, launder section, feeding, holding or casting furnace, the casting furnace itself. Okay, let's discuss about the early filtering system. The type of filter media employed can have a substantial impact on the success or failure of the filtration process. The popular ceramic foam filter that are utilized in sand and permanent mold casting have largely given way to the bonded particle filter in die casting application. The bonded particle filter is a mix of silicon carbide bonded with molten aluminum resistance glass ceramic composition that provide uh, the following advantage: high strength, long life, no degradation over long period of time. Third one is thermal conductivity, lower thermal gradients. Fourth one is enhanced filtration efficiency, reduce porosity. So we have various filtering system. All were effective, but were costly to maintain and were designed mainly for large volume of metals. Uh, a melting holding furnace, crucible ladle, which incorporate a filter, either ceramic foam or bonded particles. This application required a special crucible design and can be effective, but strict operational and maintenance procedure must be employed to achieve optimum performance. In second image, refractory vessel placed into a casting furnace, either a small reverb or pot furnace providing filtration. The refractory vessel houses one or more filter element, either ceramic foam or bonded particle. The metal is manually or automatically withdrawn from the interior of the vessel as the filtration process occurs from outside in. Another image we have display a refractory crucible containing a filter element which sits on the floor of the dip well of the casting furnace. Metal is ladled from the interior into the short sleeve. In another image, example of filter installed into outlet well of a central reverb or into either the casting section or the charging section of the casting furnace. This vertical gas gate filter spans the entire width of the well and most preferably employ the bonded particle filter owing to its strength and durability, thermal conductivity and longevity. Continue submerge and minimum draw down is required to get best performance of 3 filter, which can often remain in use 1 to 3 months before replacement is necessary. The strength of the bonded particle filter also allows it to be carefully scraped with a cleaning tool to remove excess cake buildup, thus extending its life. Okay, another image of filter, an all filter media box filter, which can be constructed in various geometric shape to fit either reverberatory or pot crucible furnace. Advantage for this kind of filtering system include high thermal conductivity with the silicon carbide construction, high strength and durability and long life capability. All side of the box do filter. This provide significant surface area available for filtration, but also high flow also capacity either during fill in or immediate refill with virtually no down after metal has been dipped out of by manual or auto ladle. Another image, we have several filter shapes that are installed onto stock tube in low pressure casting situation. To date, low pressure casting processes have been applied mainly to the production of aluminum wheels, but the process is now being explored and applied to the production of other automatic components. Stock tube filter provide filtration each cycle, plus providing some protection of the stock tube material itself, either cast iron, fused silica or other ceramic, reducing the rate of erosion. So I think this video take lot time. We reach to the summary. So if we summarize this video, the metal quality is essential to produce quality casting. Metal treatment are used to ensure the quality by either removing impurity or adding compound to the melt. Commonly used treatment include degassing, demagging, fluxing and filtration. So thank you guys, keep supporting us, keep sharing this video and keep learning till that. Thank you very much.